German engineering is this global symbol of perfection, of reliability, right? Well, this is the story of how that very pursuit of perfection created one of the deadliest high-speed train disasters in history. It's an incredible story about a search for comfort, a supposedly clever solution, and a whole series of warnings that were tragically just ignored.
So just imagine this for a second. You're on a high-speed train, one of these marvels of modern tech, and all of a sudden, a huge piece of steel just rips right through the floor, right between you and your family. I mean, can you even picture that? That's exactly what happened to a passenger named George Dittman on June 3, 1998. And believe it or not, that was just the first sign that something was about to go terribly, terribly wrong.
In just the next 3 minutes, this cascade of failures would unfold and lead to an absolute catastrophe. But to really understand how this could possibly happen on one of the world's most advanced trains, we've got to go back a bit. We need to look at a single fateful design decision made years earlier.
Okay, so let's talk about Germany's Intercity Express, or the ICE as it's known. This thing wasn't just another train, it was a source of real national pride. It was the symbol of German engineering excellence. But as it turns out, underneath that sleek, perfect exterior, a fatal flaw was hiding in plain sight. The ICE really was designed to be the future of travel. It was a system where you'd think every single detail was meticulously planned out. But, as we're about to see, even the most perfect-seeming systems can have a single point of failure. And for the ICE, that failure was, of all things, in its wheels. So originally, the ICE used what are called monoblock wheels, and it's exactly what it sounds like, a single, solid piece of forged steel. They were the industry standard for a really good reason. They are incredibly strong, super reliable, and proven over decades of use. But for a train that was all about luxury, they had one small but pretty significant drawback.
See, at 250 kilometers per hour, even the tiniest imperfections in those solid steel wheels would create this constant annoying vibration. Just picture trying to have a nice meal in the dining car, and your wine glass is rattling on the table, and your cutlery is just buzzing against the plate. It wasn't just a minor inconvenience, it completely undermined the whole premium experience the IC was supposed to be.
So the engineers, they went back to the drawing board. They had to find a solution, right? Something that would get rid of those vibrations and bring back that luxurious, smooth ride. And what they came up with was a completely new type of wheel, a design that would end up having absolutely deadly consequences. It was called the resilient wheel, and it was basically a wheel within a wheel. They took a thick rubber ring and sandwiched it between the outer steel tire and the inner hub. It was designed to act like a shock absorber. I mean, on paper, it's an ingenious design. It promised a perfectly smooth, quiet ride. It really did seem like the perfect solution to their problem. And right here, this is where you can see the crucial trade-off they made. They solved the comfort problem, for sure, but in doing that, they introduced this massive, completely unknown risk. They literally swapped proven, battle-tested durability for unproven comfort. It was a decision that was going to have catastrophic consequences. Now get this wheel design, it was originally made for slow-moving city trams, so you have to ask, did they ever really test it for high-speed trains going 250 kilometers an hour? Incredibly, the answer is no. They just rolled it out across the entire high-speed fleet without any rigorous specific testing for those kinds of speeds. It was a huge gamble. And it was about to go horribly wrong. And that lack of testing? That was just the first in a whole chain of critical failures. It definitely wasn't the last. As the years went by, these resilient wheels started to show serious signs of stress. Clear warnings started popping up, warnings that, for one reason or another, were repeatedly ignored. I mean, just look at this timeline. It shows a whole series of missed opportunities to stop this disaster. You've got a research institute raising major concerns. A tram company finds fatigue cracks in their own wheels and tells the National Railway. And even the very wheel that failed on the day of the crash had been flagged multiple times. Each one of these was a chance to prevent this tragedy, and every single one was missed.
Here was the real problem. That rubber ring that was so good at absorbing vibrations, well, it also perfectly muffled the sound of the metal getting weaker. It hid the growing cracks. And because the railway had dismissed automated crack detection systems, saying they got too many false alarms, they were relying on people doing visual inspections with flashlights. They were basically trying to find a microscopic crack on a metal wheel in the dark. It was an absolute recipe for disaster.
So now let's see how all of these things, the flawed design, the zero high-speed testing, the ignored warnings, all came together in the final horrifying moments of ICE 884. This is where engineering pride and human error collide with just devastating consequences.
And you have to remember, this isn't happening in slow motion. The train is absolutely rocketing down the track at 200 kilometers per hour. That's about 125 miles per hour. At that kind of speed, there's absolutely no room for error. None.
This is the 6-second chain reaction that sealed everyone's fate. It all starts with a tiny fatigue crack hidden for months that finally, at that exact moment, gives way. The steel ring shatters. A huge piece of it gets jammed into the carriage floor, creating this deadly metal hook hanging underneath. That hook then catches a track switch and violently flips it. The front of the train keeps going straight, but the back half is suddenly diverted onto another track. It's torn apart, and the third car slams sideways into a concrete bridge pillar, which then collapses on top of everything.
The scene at Eschede was just one of utter devastation. The investigation that came next would uncover every single mistake we've just talked about, and it led to sweeping changes that would completely redefine high-speed rail safety forever. In the end, 101 people, passengers and crew, lost their lives, with hundreds more injured. It became the deadliest high-speed rail accident in history, a tragedy that, really could have and absolutely should have been prevented.
The sheer force of the impact is almost impossible to imagine. That 300-ton concrete bridge collapsed onto two of the train carriages, crushing them down to a height of just 6 inches. It's just a horrifying illustration of the destructive power we're talking about here.
The lessons learned from Eschede were immediate and they were decisive. The resilient wheels were scrapped. Gone. The entire fleet was refitted with the original, reliable monoblock wheels. And suddenly, those vibrations they caused, they weren't seen as an annoyance anymore. They were understood to be a crucial safety signal. This disaster is now a mandatory case study for engineers, a permanent reminder of the dangers of putting comfort ahead of fundamental safety.
The Eschede disaster is just such a powerful, tragic, cautionary tale. And it forces us to ask a really difficult question. When does our pursuit of a clever solution cross the line and become a deadly risk? It's a question that every engineer, every designer, every innovator has to constantly ask themselves. Because as Eschede shows us, the consequences of getting it wrong can be absolutely catastrophic.